is mostly free flow, like if there is no bottlenecks generally for geometric design. So what we need to do is, of course, like we need to detect those vehicles. That's the main point. And I can see, I can show this 300 intersection in Toronto have this kind of unconditional traffic signal priority system already, and it's probably a couple of years ago, so it should be more than that. And expansion is like approximately 2 intersections per month. I will give some cost and other kind of things too. So one example I will show like what it can do is 504 streetcar King Transit, King bus, which is a very long route from Dundas West to Broadview and Broadview to Dundas West. We'll be talking about that. Ridership is 50,000 riders per day. Headway 2 minutes. Total number of stops 114. End of time is 60 minutes. Is total journey time 102 intersection. And as of this slide, when it was created, 32 of them was signalized, and 27 has this kind of absolute signal priority. I think it's more than that right now. So I will show what are the benefits and what we can do on those kind of things. So the basic TSP setup. The basic TSP setup is transit priority, signal priority setup is like we need to have a location before the intersection where you put this priority request. So there is a priority request loop. You can use a different kind of technology. It's not just limited to GPS. You can do many things. What you need, in the second lecture I was showing you a lot of technology for data collection, right? So the same thing with the data collection you can also use for this kind of efficiency. So we are trying to do this kind of multi-purpose technology use in transportation. So you need to detect some way your priority request loop. Whenever you are passing that, then the signal controller gets the signal, yes, I need some green extension to go for that. To go in those kind of intersection. And intersections are important because 25% of delays are due to signal time. And whenever you pass this priority signal loop, like, then it cancels those kind of effects. So that's the basic setup. So it can be magnetometer, it can be anything. It can be any kind of sensor, any kind of detection methodology, and people are coming, private sector are coming with different kinds of technologies.
Are most of these priority signals the unconditional ones? Do they automatically change the light if the other stream of traffic is going?
Yes. Let's talk about it. That's the next. Okay. Always the questions is for. So let's talk about what it does. It does three things mainly. One is green extension of the route in which that transit vehicle is coming. So green extension, but it needs to red truncate the other side, because you have to do red truncation that side, red signal truncation, right? And once your priority is given and bus passes through that intersection, you have to do also offset recovery, like that thing that you have done, like then you have to recover those kind of things. So mainly like this kind of a green signal, and maybe green signal was there, you give some sort of signal priority, and then red truncation, and then offset recovery. I will give a little bit more clearer picture here, like how we do it in signal timing. Okay, so let's assume like this is our original signal timing. Transit corridor green, amber, and all red. So that's our signal timing setup, like we started seconds. And there is also a pedestrian one. We have to also be looking for that. There is a walk time and then flashing, don't walk, and then don't walk when you start the amber, right? So that's how the usual, like any traffic controller system, will be putting your system together, right? So there is a point where you can make this decision for signal, which we call is extension decision point, right before flashing don't walk, because you need a minimum time, like for those who are already pedestrian on the roadway, have them given some sort of time to clear the road space out. So it's complicated in a way, but the principle is also simple. I will explain how we do. For example, what we can do is, since we know this is our decision point, extension decision point, we can either offer a fixed length, extra time for green signal, and then have a demand-dependent green extension, meaning that we will be waiting until we know buses pass those cancellation loop, tell us that we passed the intersection. So this is what they do. So that you need to then have a fixed length, to take care of these mandatory flashing don't walk signal timing. Then we can demand dependent. So this is one way of doing it. Go ahead.
So how they count the volume? Does it happens with the volume? If the volume is high, then they are making the green extension.
No, there is no relation with volume, because it's public transit bus. We are giving extension to only bus asking for the priority signal, and then it passes, we give. So bus is our concern on that bus passenger transit corridor green sign. But you're right, that's the unconditional and adaptive. I will come that can we learn other issues like traffic? That's more complicated than this usual one, which is already in practice in various cities. And we have in Halifax too, I believe, in 159 corridor, bus rapid transit corridor, the Metrolink Portland. I believe they have queue jump and one or two intersection. Look at their 5 years plan, last one. I believe they have explained these kind of things very well, and for your project that is an important reading as well. I believe that's in our course website already. So they probably have at least a couple of intersections for these kind. So this is one way of doing that. So green extension. The other way is just being more the demand dependent green extension comes first and then a fixed length. So that is another way of doing those kind of things. This is a better one in a way, how much time you need for this bus. Once it's passed, then you give the fixed length. So it depends on the scenario. You have to do some of those traffic counting and really understand what is the impact of which kind you choose.
I guess there'd be a benefit of switching to a GPS system where you could probably come up with a model that's more continuous rather than just start end with the signal priority. It's if you can see where the bus is and how fast it's moving, and then you could have some kind of algorithm that decides when the flashing don't walk happens to maximize.
That's the conditional. That's the conditional and adaptive system. But that is more costly. That is more intensive. How to implement those all kind of things. This looks more kind of usable, easier. If someone wants to put some money on it. But yes, and even for this we need GPS. GPS found a better kind of a signal requesting technology and signal cancelling technology than other treadle mat or infrared or other kinds of things, intrusive kind of thing, which is sometimes unreliable, sometimes there are weather conditions, sometimes many other, as you know from our earlier lecture. So GPS, even for this one, we need GPS. GPS is the most proven and effective technology even for this one. So that the GPS is telling, maybe not in the signal controller, they can just emit the AVL system, that one HRM is getting. They put it in the control station, and if we have some control communication system with our controller, then we can automatically we do that. So that's automatic too. So GPS is more reliable because it's so far we haven't seen much disruption in terms of GPS detection, except probably Iraq war, when all the satellites went to the Iraq and people are getting issues with getting signal GPS signals. but generally, like right now, dedicated, like we have separated civilian use of satellites and military use of satellites. I think there is no issue, at least at this point. I don't see any problem with those kind of things. Now, the other thing is, like, we need to also do that red truncation, like, because we have to now also, like since there is no bus, we can truncate our red a little bit. So let's say red truncation is a little bit more than the flashing don't walk, and usually for 5/8 of minimum green time is used as your walking time for those kind of things, and minimum walk interval should be 7 seconds, and these are also, like, it needs to be confirmed with your road configuration, like it depends with 3.5 meter lane versus 3.7, 3.1, and also it depends on what kind of pedestrian you are expecting, like wheelchairs and other kinds of things, but this is a more kind of a general kind of things, so we need to truncate those red, what we gave as an extension for that particular signal timing, because all signals are already designed for green wave. So we need to go to that old mode. So we start truncating red for the transit corridor if we don't have transit vehicle in it. And also the red truncation is important. So before truncation, for example, this is in the side street, so side street green, so you need to offer, like you can do both ways, like you can truncate in this side, extend in this side and truncate in the other side, but you need to always keep in mind that there is a minimum green time that we need to offer, particularly for pedestrian, which must include 5/8 of minimum green time with flashing don't walk and minimum walk interval. So you must need to satisfy these conditions as long as when you are cartling. And sometimes this cannot be done like, oh, this is not offset recovery yet, sorry. So you need to truncate that other side, making sure like green extension is not being disrupted. Okay, so that's the basic principle, and that's what everybody is using. And then this is offset recovery. Then you cannot all at once like come back to the original green wave signal. You have to do it sequentially, like some. So you have to do one at a time. Otherwise, like you cannot do all at once. You might get the queue in the other street, like the side street. That's meaning for the transit. So you have to do that, and it depends all on that particular signal that we are talking about. So there is a lot of planning involved, planning and engineering, signal timing, those kind of things. So that's what we should be doing. So before offset transitioning, so what we need to do in the offset recovery is shortening. So your green signal, you are shortening. Like once there is no car, no public buses, then you start like shortening green to go to that normal operation. There are some risks of having traffic disrupted. That's why we need a really very careful consideration of how much delays or queues we can afford to develop when we are offering this kind of extension, particularly for the side streets. Like that's one thing. The basic principle is make sure you have minimum walk time. That's the basic principle. You must confirm that exists in your signal time. And we can test those kind of things in micro simulation tools. For example, this lab is probably within a month getting all those things. We have ordered that. So you can also test, like if you are changing that signal timing, you can test whether how much you are improvising and what will be the delays, what will be those kind of things. So VISIM, not VISM, VISIM, V-I-S-S-I-M, VISIM is for this purpose. Like you can do corridor by corridor analysis, and like you need to put those signal timing scenarios. It's the same ME3, the one I discussed in the last class, same kind of scenario based technology. So you put your business as usual signal timing, and then you shift, and you know your flows, you know everything. then you shift your scenario, change your scenario and try to see whether you are improvising those kind of things. So that's what it does in these kind of things. And of course, like in the offset recovery, you need to do both. Shortening in the green, the transit corridor side, you need to shorten your green signal, right? Green, because you have given the extension. On the other side street, like you need to lengthening that piece, side street piece, like you have to lengthen so that you go to the normal operation. And these slides are available to in the website. I think for a long time you have that. Now, what happened for this kind of speed? As I told you, like in Route 1504, the streetcar, the journey time was 130 minutes. With this signal timing, signal priority system, it reduced to 117 minutes. It reduced the fleet requirement. You guys probably are not aware of, like, it's not always like one bus is running in the same line over and over again. There is an optimization tool people use to schedule the vehicles in different places. It actually reduced the fleet size, so which is an important one. It also improved the flow of traffic along transit corridor. And the cost saving was 1 to 2 fewer streetcar reduced annual saving of 200K plus annual operating costs. So this is simply just savings on the fleet size. Savings on the fleet size, and annual operating cost is not accounted for. It reduced a lot. And payback in less than 5 years, cost is generally 15,000 to 25,000 per intersection, and 500,000 to 850,000 per route. Of course, it depends on how long your routes are. So it's a very good rate of return if you are really interested to improve public transit system. Now, I think still we have these kind of reliability issues, large headway variables, and like still there are issues with the side street traffic, like the car traffic, because when you are giving priority extension for buses, there will be always like there is always trade-off, like it's all about like decision making. So traffic will usually get disrupted. Sometimes significant green time is burned while streetcar is loading and unloading at a near sided transit stop, affecting adversely crossroad traffic. So this is for the streetcar. Like if you have a near side intersection transit stop, then that can be a cause because you are detecting that transit is actually asking for priority signal. Actually, it's actually loading and unloading, so the entire dwell time can get problematic. So those kind of things are usually problematic. Even though if we do a lot of planning kind of signal timing, there could be this risk of corridor signal disruption. The green wave that we usually try to offer to reduce the queue and improve our efficiencies. So that could be another like ongoing issue. That's why people started looking at, can we do this kind of conditional or adaptive TSP? Meaning that we start not only requesting and blindly offering extension and retruncation, we also collect the volume of traffic in both sides of the street and have an algorithm within that to make best use of like the traffic extension or reduction as we can based on what we can afford without creating long queues and other kinds of things. And also, like for example, Professor Amr Shalabi, who was my public transit professor, his research is all about this adaptive transit priority system. Can we learn, instead of like a human offering what should be the signal inputs, can we create a system that can learn over time, like collect data. Learn over time means collect data 24/7, maybe entire whole year, and really learn, give a reward basis, like machine language kind of, like those who are aware of machine language, like it's intelligent system, AI, artificial intelligence. So his research is all about that. So how we can improvise on these kind of transit priority signal. And I believe a couple of California and major city are already utilizing some advanced kind of commercial product that has this conditional and adaptive TSP, but it requires this advanced traffic management system, meaning that you need to have eyes on the road system. It's different than in urban planning, eyes on the street. It's eyes on the road system. You need to collect information in various cities, and I think these things are more appropriate for big cities where congestion is a big issue. I don't see in the very near future we will see that kind of system for Halifax, but those who are interested to work in big cities, you might come up with these kind of issues people are dealing with.
So would that be more when you've got a lot of traffic going in kind of all directions, whereas with Halifax, usually during the peak hours, like probably more kind of going down one corridor or a couple in the same direction?
Same direction for multiple lanes, like 401 makes sense, like 10 lanes, right? Or Gardiner Expressway, or Young Street, like those things. In my opinion, that makes sense. The investment of putting those advanced traffic management system, so that we don't only have the traffic volume information on intersection. We have mid blocks. We have other which can also feed information into these kind of adaptive traffic transit priority corridors, so that we can make sure the queue length, like here, like the unconditional one, I was just putting this idea in. Whenever you see someone asking for priority, you are giving it, but those kind of conditional and adaptive will be making more constraints in. Like we will not allow queue building in the side street, say 10 car or 50 car, whatever. You got my point? So just making sure like there are other constraints into the equation. But for that we need a lot more better traffic management system. And this is the reference, like I was talking about, more advanced way of doing these kind of things, prediction model of bus arrival and departure times using AVL and FTC data. And one of Hisham was working also as a part of his PhD on one of the coursework, like to look at these kind of things. So there are researchers going in that direction. But generally speaking, we are already utilizing the unconditional, active signal priority, and which is very important, particularly for BRT. So whenever we are talking about BRT, if we can't give exclusive right-of-way, we should be looking at technology-based active transit priority, TSP, transit priority signal processing, or we can also do design solution. So this is one technology. You can also do the design solution, which is queue jumping. Like you have queue jumping in the intersection, like in the McDonald Bridge. You have seen that, right? There is a queue jumping lane for bus rapid transit, 159. So that means the bus comes, so just there it comes in front of those kind of things. Active transportation is also using those kind of things, like the bike boxes in the intersection. These are all to reduce the delay in intersection. Intersection is challenging for any kind of traffic, but in my opinion, this is also the opportunity where we can exploit more planning and try to make better use of our time. Okay. So this is a feasibility. So we can do the design solution, we can do this technology solution. It's not very complicated. It's just requires some sort of like prioritization, where which mode we should be giving priority, or in my opinion, let's start thinking about making level playing field for all modes. Right now, it's all about car. We plan for car, we design our roads for car, we think about like anything whenever we have a transportation problem, we start looking at it. So these are the solutions, this is also branding opportunity in many ways. Like we have a transit priority signal, like that alleviate like the preferential treatment for transit. Transit is not simply a social service or a central service, right? So you get those kind of like branding kind of things. Branding is not about just simply having a better logo or better things. Branding is also operational efficiency and talking about it. So that's important. That's important. So that is in general like what I tried to cover in this class. Please read the transit 5 years plan. At least scan it. And there are one particular section about this transit priority signal. You'll probably see the similar kind of things that I'm teaching here, but that will be a helpful guide when in your project, when you are will be talking about BRT package, like you may be able to come up with a couple of those ideas. Any question on APTS? Sounds good? We got it so far? So that's the first half of this class, and then I'll give 10 minutes break, and we'll come back and talk about the summary and try to talk with you about your project and anything that you want to discuss a little bit more elaborately. Okay, thank you very much.
Have the tests been marked yet?
No. Okay, thank you.